All right, this week we're going to talk about calorimetry and enthalpy. Um, and basically what we're going to be doing is calculating how heat is transferred. Um, in general, we need to look at a chemical system where heat is absorbed or released, and we measure um, that amount of energy based on the temperature change. And it's generally the temperature change in the surroundings, which in our cases will most likely be water. Um, and that's how we measure that. Use the symbol Q for heat of reaction. Um, and it can be used for either the amount of heat absorbed or the amount of heat released. We use the sign, remember, to determine which direction that goes to. Um, if the system is losing energy, so it's an exothermic reaction, Q is going to be a negative number. If the system is absorbing energy, then Q will be a positive value. So in a physical system, we remember that Q lost by an object or substance is the Q gained by another object or substance. And that's simple physical heat transfer. In a chemical system, the Q produced by a chemical reaction is the Q gained by the object or substance. Or the other way around, Q absorbed by the chemical reaction is the Q lost by the object or substance. And so that is the basis then for what we use in terms of calorimetry. We're going to use our Q equals mc delta T equation again, where Q is our heat or energy, M is our mass of the substance, C is the specific heat capacity of that substance, and delta T, of course, is the temperature change. Now, you've always got to be careful what it is you're actually measuring the change in temperature of, because that's going to dictate the values of C and M. Okay. All right, let's do an example here. So calculate the energy required to raise the temperature of 300-gram sample of water from 20 to 26 degrees Celsius. So Q equals mc delta T, 300-gram sample. Specific heat capacity for water is 4.18 joules per gram degree Celsius. And the temperature change, 26 minus 20 degrees, 6 degrees Celsius. So we get 7,524 joules. Remember 3 sig digs, right? Yes, I know the 300 is ambiguous. I like to go with 3 sig digs on this one. I'm going to try and avoid that ambiguity in questions that I give you. Your textbook isn't always so nice, so I thought I'd introduce this idea again. Remember that from grade 11. Most textbooks would consider this to be one significant digit. Physics teachers will also say it's one significant digit. We actually know it's ambiguous. In other words, you don't know if it's 1, 2, or 3 significant digits. And so as a result, I'm going to assume the greater value, and it makes things a little bit easier and a little bit nicer in the way we handle our final answers. So 3 sig digs, so that's going to be 7.52 kilojoules. All right, how much heat is absorbed in a 60-gram copper wire when its temperature is raised from 20 to 80 degrees? The specific heat capacity here is given as joules per kilogram degree Celsius. So make sure that you understand that that's got to be converted to grams per, joules per gram degree Celsius. All right, so again, Q equals mc delta T, plugging in our numbers. We get 1,386 joules. Again, 3 sig digs, so 1.39 kilojoules. Okay. Remember last note we introduced the term enthalpy. Okay, so this is also a term that can be used here. Sometimes enthalpy of reaction is used for calorimetry type of questions. or enthalpy of solution, or enthalpy of combustion, those kinds of things. So what's calorimetry? A calorimeter is simply a device that we use to measure these temperature changes under the reaction conditions. It allows us to kind of trap all the heat and figure out exactly how much heat is transferred. You can get industrial calorimeters called bomb calorimeters, usually with big metal containers, little reaction container inside, very thermally insulated to the surroundings. And so all the heat is given off or absorbed by the reaction comes from the calorimeter itself, or stays in the calorimeter itself. Basically, we take those reactants, then put them into the bomb part of the calorimeter, the reaction vessel, and then it's sealed up, and the reaction is set off. Any heat liberated or absorbed by the bomb from the water is then the temperature change is measured, and there you go. This is kind of what they may look like. Really good and expensive ones have a motorized stir rod to keep the heat fairly even in this water surroundings. The bomb itself is another sealed container. Electrodes usually used to set off the reaction. The really expensive ones will have a thermocouple rather than a regular thermometer, but same idea. Okay. You may have an oxygen inlet here. Make sure that you have a pure oxygen environment to carry out the combustion, that sort of thing. We have one of these, but they are very expensive, so maybe over the years we'll try and build up a class set, but that hasn't happened yet. So we generally use one of these guys, a styrofoam cup calorimeter. Usually has lots of air to talk about in your write-ups. And sadly, we won't be doing these this year. But here's, usually we nest a couple of styrofoam cups, and then rather than a cork, we'll use another styrofoam cup set upside down over the top, and then punch a thermometer through there. Because we're usually doing reactions such as, well, not even reactions, heats of solution type of thing. And if you're only stirring something or that's just dissolving, then you can get away with using the thermometer as a stir rod, but normally that's not done. You really don't want to break your thermometer and then start over again. All right, then we have this idea of molar enthalpy. Remember from grade 11, the mole, yes, it's coming back to haunt you. Generally, we reduce things back to a molar value. And so the molar enthalpy is simply the enthalpy change that's taking place per mole of the substance. Similar to what we did last year with all this molar mass, molar volumes, all that kind of stuff. We again represent the enthalpy change, so delta H, and then we use a sub X value where that represents the type of reaction. So molar enthalpy of combustion, molar enthalpy of reaction of some sort. So for example, this one, molar enthalpy of combustion. We will use, and this is where it gets a little bit confusing, is the molar enthalpy and the enthalpy change. We use the same symbol for it. And so it's kind of important to understand specifically which is which. Right? So in this case, molar enthalpy of combustion, delta H sub X, times the number of moles would give you the molar enthalpy. Quite often that molar enthalpy won't have the X subscript, so that it's kind of not confused with the molar value. You'll understand what I mean once we start getting into a few questions. So let's try this one. Combustion of hydrogen gas to make water. So this reaction generally gives off, for every mole of water, you get 285.8 kilojoules. That energy term can be included in the reaction equation. This is something you haven't seen before. The other thing that's different about here, and you may or may not have seen before, is we're now using um, fractional coefficients. Fractional coefficients is not wrong. Up to this point, we've kind of shied away from using those. It would have made combustion reaction um, balancing in grade 11 a lot easier, but we like to get people used to dealing with the fractional issues. And some people really have a problem with fractions, but now you have to kind of get over that. So grade 12, going on to university, fractions are your friend. Get used to using them. Start getting comfortable with them. This is where we're going to start using. All right. So this is a thermochemical equation. You'll notice it because it's got the energy term in it. And the reason we use the fractional coefficient here is because we want to know that this value here is for 1 mole of hydrogen making 1 mole of water. That's important, 1 mole of water. And so for every mole of water, we get 285.8 kilojoules of energy given off. That's why we have to have that fractional coefficient there to make sure that this is a 1. If we used whole number coefficients here, then this would be 2, 1, 2, and this number would be twice as big. Okay, so that's important. This number has to go with the coefficient that's involved here. Right? So in order for this to be a molar value, kilojoules per mole, this has to be a 1 coefficient in front of the water. All right. Now, why is this a negative value? Because this is on the product side. Okay, so it's an exothermic reaction. So the system is giving off heat. The system is losing heat to the surroundings. As a result, the enthalpy change, therefore, is a negative value for it. Okay? So what this symbol means, the way we read it, is the molar enthalpy of combustion is negative 285.8 kilojoules. And it is a per mole value. Okay. All right, sample calculation problem. The first one, Freon 12 has a molar mass of 120.91 grams per mole, is common refrigerant. Energy is being transferred from the inside to the outside of the fridge. If 500 grams of Freon is vaporized, what is the expected enthalpy change of vaporization? It is expected enthalpy change of the molar heat of vaporization is 34.99 kilojoules per mole. All right, so how do we figure this out? First of all, we need the number of moles. All right, so if we look at Freon, has the molar mass of 120.91 grams per mole. Mass divided by molar mass gives us our 4.135307, a bunch of decimal places, moles. Our enthalpy change is going to be the number of moles times the molar enthalpy of vaporization for Freon. So this number here times the 34.99. And so that's going to give us 144.6944 in a bunch of decimal places kilojoules. Looking through the values, we're going to use 4 sig digs, 144.7 kilojoules. Question number 2. In a calorimetry experiment, we've got 7.46 grams of potassium chloride. We dissolve that into 100 milliliters of water at 24.1 degrees Celsius. Once we're done, the final temperature of the solution is only 20 degrees Celsius. What's the molar enthalpy of solution for potassium chloride? Right, so notice right away that the temperature is going down. Right, so the surrounding water temperature is going down. That means the system is absorbing water, so we're going to have a positive enthalpy change taking place here. All right, so delta H equals, in this case, it's going to be negative Q, right? Because the system is losing energy. So negative MC delta T gives us 100 times 4.18 times negative 4.1. And so that's going to give us the 1.71 kilojoules. And the reason I put the negative sign in the front here is that, right, because the water is losing energy, the system is gaining energy. So it's going to be the opposite value. Right? So we have to manipulate our equation a little bit so that our delta H of the reaction, in this case solution, is going to be the opposite of what happens to the water. That's why the negative sign. Right? The temperature change here is for the water, right? This is the system, and so therefore the sign has to be negative for that. Figuring out the molar enthalpy then, once we have the amount of energy. We're going to take the mass divided by the number of moles to give us mass divided by molar mass to give us the number of moles. Now we're going to take the number of moles times our enthalpy change, and we're going to get our 17.1 kilojoules per mole. Okay. Again, notice that I did not round this value here. I left that in the calculation here with all the decimal places, and then rounded at the very end. Okay. So make sure that you carry those numbers through with all their decimal places. Round at the very end. Don't round partway through and start using rounded numbers in further calculations. Your homework then is found on these pages. That should take care of this week. Next week we'll be introducing an energy assignment, and that will be your major assignment for this unit. Good luck. Ask questions as they come up, in your email or on the discussion page.